We've been talking about nucleophilic sigma bonds, and specifically alkali organometallics, where we have bonds to elements over here that are extremely electropositive, carbon-lithium bonds, carbon-sodium bonds, carbon-potassium bonds, not so much those. But let's go ahead and keep talking about the reactivity of these bonds. You would predict, just based on bond length, that carbon-potassium bonds would be more nucleophilic and more basic, that carbon-sodium bonds would be more nucleophilic and more basic, and you would be right. And so why don't we use alkyl sodium or alkyl potassium species? Why do we always use organolithium so much, or Grignard reagents? Well, let's go ahead and take a look at what happens if you try. You won't see the full, the full scale of problems if you try to use carbon-potassium bonds, but let's go ahead and see what happens when you do organometallic addition to carbonyls. That's the #1 use of things like organolithium reagents or organomagnesium reagents. So if you take these various different phenyl lithium, phenyl magnesium, phenyl sodium species, and you add them to a carbonyl, I would hope that you would be able to guess what happens here. You would take this nucleophilic bond here and you would add in. And if you're doing that with a Grignard reaction, you've probably done that you might be doing that in the organic chemistry laboratory course that goes, or have done that in an organic chemistry laboratory course. It's called a Grignard addition. You'll get pretty decent yields of CC bond formation to make tertiary alcohols in this case. And in this case, the yield would be 97% yield. The problem with this reaction, when you add to carbonyls, in most cases, is that there are also CH bonds here. And those CH bonds can be deprotonated, right? The same highly nucleophilic species that are going to attack the carbonyl can also deprotonate and then push the electrons. Let me use a different color of pen because I don't want to confuse my arrows here. You can also deprotonate and push the electrons into that same carbonyl. So which is faster, CC bond formation by adding to the carbonyl, or deprotonation to make an enolate? Well, if you use a Grignard reagent, you don't see any of this enolization, fortunately in this case. And this is a system that is very easy to make the enolate, because when you deprotonate next to the carbonyl, you end up with conjugation. This double bond in the enolate is conjugated with the benzene ring, and it makes just putting a simple phenyl group next to the carbonyl makes it more likely to have this enolization problem. And that's frustrating if you're trying to add to the carbonyl. If you do phenyl lithium or phenyl sodium and potassium, you start to see competing enolate formation. How bad is it? Unfortunately, in this system, they had to use not a regular solvent like an ether solvent. Those are typical. So these results may look a little worse than normal. But if you just take phenyl lithium in a non-ether solvent, like benzene or hexanes or something like that, what you find is you don't get good results here. You only get 14% yield of the desired addition. The rest of the material that you're getting there, or at least that you can isolate, you get a 75% yield of enolization. It's very hard in some cases to stop this competing enolization. And if you go to more reactive organometallics, it doesn't get better, it gets worse. This problem of enolization gets worse. So if you go to phenyl sodium, now you're getting 4% of the desired CC bond forming reaction and a 60% yield of the ketone that would result if you try to work up the enolate just by dumping water in there. You don't get good results. You start to see a lot of acid-base, not that there's any acid, you just see a lot of basic reactivity. And when you go to, it's just as bad with the phenyl potassium. You see 0, or maybe worse, 0% of the CC bond forming reaction, and it's all deprotonation. In fact, phenyl sodium, you can't put that into ether solvents. It'll start to deprotonate the solvent. So that's why. Under more typical conditions, if you just add phenyl lithium and you're using THF, which is a typical solvent, you'll get about a 60% yield with phenyl lithium of this CC bond, and you'll get about 30% of the enolization. They don't tell you that. Usually they just tell you, oh, you got a 60% yield, and they don't tell you what the other stuff is, right? So we don't tend to use these super reactive bonds, carbon potassium, carbon sodium. They're just too basic. You're just going to see a lot of deprotonation chemistry that you don't want. What we want in organic chemistry is to make CC bonds, not to deprotonate, right? If we want to make the enolate, we'll use LDA for that and have very good control over that. Okay, so that basicity high reactivity means basicity, unfortunately. So the carbon lithium and the carbon magnesium are a good compromise. Now, how do you make alkylithiums? What did you learn about if you took an introductory course about how you make alkylithiums? Let me show you how you would make a simple alkylithium like methyllithium or butylithium, or sec-butylithium would be another common one. So what you do is you take lithium metal, and if you work out the stoichiometry, you'll end up using two equivalents. Not really, it would be one equivalent. You'd use 200 mole% lithium for every mole, 2 moles of lithium for every mole of the alkyl halide, of the alkyl bromide, the alkyl chloride, the alkyl iodide. Now, how do we draw out the mechanism for this reaction? I'm not going to ask you for the mechanism. I'm not going to ask you for the mechanism for how to draw out the arrow pushing mechanism, because we don't have a lot of time in this class to talk about radical chemistry and radical arrow pushing, unfortunately. But it's more complex than that. So if we draw out the mechanism for this process, how would we do this? How would we depict this using the kinds of rules that we draw out in this class? So one way that you might do it is you might just draw lithium next to the arrow and just put a dot there, right? Lithium, just a lithium atom has an extra 1 electron associated with it. It would like, right, doesn't really want that electron. It's going to donate it to something. And so how do we depict that? So when I draw the product of what happens when that lithium gives up its electron, how am I going to depict the structure of this product? And sometimes people will write this out as lithium plus, comma, E minus, just because they really want to show that the lithium wants to give up that electron. Now, I've got a problem here. Whoa, I didn't mean to draw lithium. I'm getting a little bit ahead of myself. Let me just erase that. Let me just erase that lithium. That's supposed to be that same chloride atom, chlorine atom. Okay, so I have a problem here. How am I going to depict this when I give an extra electron to this simple organic halide? I don't want to put an extra dot over here on the chlorine. That would look crazy. We don't typically put 9 valence electrons on atoms, even chlorine. There's no way in the world I'm going to put 9 electrons on carbon. That is fundamentally impossible. And so what we do, if you're trying to draw an arrow pushing mechanism that doesn't break any of our rules, is we typically, for these types of species, we'll put brackets around this and then just put a dot. And we're not going to say whether it's on the chlorine, we're not going to say whether it's on the carbon, we're not going to say any of that. We're just going to say there's an extra dot in there. And if there's an extra electron, that means there's also an extra negative charge. We don't have a good Lewis representation for this species, which has picked up an extra electron. We don't have a good Lewis representation. Let's talk about what's really happening there. If you put an extra electron into that system, right, you're going to end up with lithium plus left over somehow, or the equivalent of that. Let's go ahead and take a look at that carbon-lithium, the frontier orbitals in that chloromethane molecule. Right? If I draw the frontier orbitals for that chloromethane molecule, it starts off like this. If you do an SN2 reactions and you put 2 electrons into sigma star, you'll break the bond. That's what it means to add to an antibonding orbital. You break the bond. But if I put 1 electron into this system, where's it going to go? This is the only place it can go. That's what happens when you dump an electron in there. You put 1 electron into the antibonding orbital. Is the bond broken? Kind of. It's longer. Is the bond all the way broken? No. Is the bond part way broken? Yeah. So people try to find all kinds of unsatisfying ways to deal with this. Some people draw a dashed bond here. Some people draw an electron just floating around so they don't know what to do. So we don't have a good representation. So don't freak out over this. I'm never going to ask you this mechanism, but I want you to have a clear understanding. We put an electron into an antibonding orbital, and so this bond is going to get long, it's going to get weak. We can push arrows starting inside this bracket here and just go like that. That's what's going to happen. We weaken that bond. It's going to be easy to break, and so it's okay if we just draw it like this, and we lose chloride minus according to my arrow pushing. Right? That extra dot, now that extra dot I had outside the brackets, that extra dot, let me paint it in blue over here. That extra dot that was outside the brackets, now I can just put on that carbon atom. And then you'd end up with a chloride anion just floating around, which is nice because we have a lithium floating around looking for something to do. And if I want to draw the next step of this process, I can just draw that interacting with the lithium dot. And you could use some kind of arrow pushing, the half arrow pushing now for radicals. Sorry, I didn't leave a lot of room here. Boy, that's not a lot of room I left. And anytime you have two radicals, they at very fast rates want to rejoin to make bonds. Okay, so I'm not going to ask you this mechanism. It would be a similar mechanism if you did a Grignard reaction. You transfer an electron into an antibonding orbital. You end up with this radical anion that there's no good representation for, and there's going to be a mixture of regular arrows and these half arrows in your mechanism. So you might guess, when you look at this orbital diagram over here, you might guess that not all alkyl halides are equally reactive when you make Grignard reagents or alkylithiums. So let me just remind you that if you look at sigma star, that's where the electron's going. If you look at the energies for sigma star for carbon iodine, let me draw that long bond there, sigma star for carbon bromine, sigma star for, let me make that a little less long, for carbon bromine, and then sigma star for carbon chlorine. You might expect that alkyl iodides it's easier to put an electron into an alkyl iodide antibonding orbital. If you want to make an organolithium or a Grignard reagent, or alkyl iodides are better, faster. It just works faster. The bond's weaker, sigma star is lower, so you'll get the fastest rates for electron donation for that initial reduction and the overall rates for formation of organolithiums and organomagnesiums if you start with alkyl iodides. Unfortunately, it's not always that easy to make alkyl iodides. It's easy to make bromides and chlorides, and so most people go with the bromide because it's pretty easy to make selectively, to make alkyl bromides selectively, and they have good rates. And not quite as good as carbon iodine bonds, but the alkyl iodides are best. So, in practice, this is not really relevant to what we talk about in this class, this kind of synthesis of alkyl lithiums from alkyl chlorides, because I don't know of anybody who's ever taken an alkyl chloride and used it to make an alkyl lithium here at UC Irvine in my 20 years here. Nobody would do that. It's just not. Why is that nobody would do that? Because they are a pain. You have to have special equipment, special stirring rates, all kinds of weird side reactions. What we do in our labs here and all around the country and all around the world is we buy probably about 4 common alkyl lithiums, and we make all other lithium compounds starting from those. You can order a train car load full of alkyl lithium solution. It's not that expensive. It's made on an industrial scale, but if you try to do it on a small scale in the laboratory using this method with lithium metal, you'll get lousy results. So how do you take an alkyl lithium that's one of these cheap ones and use it to synthesize another alkyl lithium? Let's go ahead and talk about one of the most common ways. There's a number of multiple ways, but the most common way in a typical laboratory environment, this is a medicinal chemistry lab at some pharmaceutical company, they wanted to make this alkyl lithium compound right here. They wanted to make 2-furyl methylfuran, whatever, lithiomethylfuran. And so what's the way to do that? You start with the bromide or the iodide. That's easy to make using electrophilic aromatic substitution, and then you just add butyllithium. You add butyllithium to the alkyl bromide, and you get the alkyl lithium. Now, what's going on there? You've never seen that before. You can just take an alkyl lithium and add it to an alkyl bromide, and it turns the alkyl bromide into an alkyl lithium. Not lithium metal, butyllithium in this case. So let's talk about mechanistically what's happening, because there's, based on what I know, you have no idea what's going on in this reaction. So the first arrow is going to start with this butyl lithium bond, and where are we going to put those electrons? Here's what we're going to do. We're going to attack the bromide, not the carbon. No, don't do that. That's like SN2 type thinking if you do that. We're going to attack the bromine, and we're going to get an intermediate out of that. We're not going to break any bonds. You don't have to break a bond. Bromine can have more than, you can have 7 bonds to bromine. You can buy salts, bromate, perbromate salts that have 7 bonds to bromine. That's not impossible. But I'm going to take electrons away from the electropositive atom, and I'm going to give the electrons on that butyl. They will be now attached to the bromine. This is the intermediate that you get in this reaction. And I don't think this will be a comfortable looking intermediate for you. Let me just remind you, there were already 3 sets of lone pairs on that bromine, those valence lone pairs. Let me just draw them there, just so we're clear, they're still there. This is no problem for bromine. It's no problem for iodine, no problem for chlorine. That would be a big problem if this was fluorine. You can't have more than 8 electrons on a second row atom like fluorine. This would be impossible, but nobody tries to do this starting with aryl fluorides. And we also have this lithium plus cation floating around, right? We took electrons away from lithium. Now what is likely to happen here? What do I know just by looking at this structure? The bonds to bromine are nucleophilic. That's what I know. It's got a negative charge. The bonds to bromine are nucleophilic. So it would make perfect sense if you said, you know what? I'm going to take the electrons away from bromine and I'll give those electrons back to the lithium. Well, that'll take you right back to, I'm not going to draw that arrow pushing. Both bonds to bromine are nucleophilic. Half the time this butyl bromide bond attacks the lithium and takes you back to starting material. The other half of the time it's this other carbon bromine bond that attacks the lithium. Don't attack the charge. I'm trying to avoid attacking the plus charge. And so what that does is that now takes you to here. And this is fully reversible. There is nothing stopping the product from doing exactly the same thing. All of this is happening reversibly. Oh, I don't want to break that carbon bromine bond. So that would happen reversibly. So this process, we call this lithium halogen exchange. You're exchanging the lithium and halogen between 2 molecules. Is completely reversible. And you're just relying on the equilibrium constant to determine whether you get a good yield or a bad yield. So when you take an aryl iodide or an aryl bromide and you just treat it with butyllithium, you're going to set up this exchange. The key to this reaction, having it work well, is to keep the temperature low. Keep the temperature dry ice, freezing minus 78 degree temperatures. If you do this at room temperature, you're going to get a lot of deprotonation chemistry, other stuff you don't want, right? We keep the temperature low. This process is fast at a minus 100 degrees, right? So you want to keep the temperature low so you don't get SN2 or E2. You'll still get a little bit of that. We'll talk about that. And so this is typically the way we make alkylithiums. We don't take lithium metal plus alkyl halides. It's just not what people do. And then once you have your alkylithium, you can take this whole mixture and then you dump in your carbonyl. It's like pretty simple. So you would take that mixture you just made, that equilibrated mixture, and you take that mixture of alkylithium, like this one, and then you just add in your carbonyl compound, and now you're ready to make CC bonds. So this is how we make alkylithiums. We take butyllithium, we add it to an aryl iodide or an aryl bromide, and that's how we make urolithiums. Now, if you're paying attention, you might be thinking, whoa, wait a second. You know, I got this O minus here, and I've got this butyl bromide byproduct that I don't really want, but it's left over from the butyllithium. Aren't I going to see some sort of a SN2 reaction? No, SN2 reactions are not good reactions. You might get a little bit of that. Maybe you'll get 1% of that unwanted as that just sits there. Well, don't go off to lunch. Work it up early by dumping water in there so you don't leave that alkoxide sitting around with the alkyl bromide. That's not the fast process. The fast process that's going to happen if you go off to lunch instead of dumping in water to your reaction is you're going to get E2 eliminations. The alkoxide is going to deprotonate the alkyl bromide, and you want a proton on the O minus anyways. You're going to dump water in there later. That's no problem if you get E2 eliminations. The biggest problem with this reaction is that as you're forming alkyl bromide in the reaction, as you're forming this unwanted byproduct of this process, the butyllithium will start doing E2 eliminations with that and SN2 reactions. And so this is a big problem, is that as you're generating this mixture, the butyl bromide will start reacting with your butyllithium. And we have a trick for that. I'm not going to talk about that trick to get around that, but this is the basics of metal-halogen exchange, one of the most common ways for us to make alkylithium compounds from simple starting materials. Now, let's go ahead and talk about this equilibrium process, because if it's equilibrium, you don't want to end up with a 1-to-1 ratio of butyllithium and phenolithium in there. And so we can easily predict where that equilibrium will lie. Butyllithium is by far the most common reagent for, it's the least expensive. Everybody has bottles of butyllithium in their lab that we use. It's very inexpensive. If you take butyllithium and you treat it with an alkyl iodide, you'll generate this equilibrium. As long as you keep the temperature low, you can avoid typical side reactions, like E2 or SN2, and you'll get this fast exchange. And so where does this equilibrium lie? Well, what you want to do is you want to use the most nucleophilic alkylithium possible because it'll drive the equilibrium to this other side. It'll drive the formation. Starting off with more reactive alkylithiums will help you drive the equilibrium towards less reactive, but still reactive alkylithiums. And I've shown you a table here that shows alkylithiums of increasing reactivity. Generally, the more P character, sp3, in the bond, the more nucleophilic. sp2, not as nucleophilic. We already know that. More P character, more nucleophilic. But it's also the alkyl substitution, right? These tri-substituted, these quaternary alkylithiums, or tertiary alkylithium, if you want to make an analogy to a carbanion, are more reactive than just a primary alkylithium. Not by a little, but by a lot, by an insane amount. So you're getting a sense here for just how much stronger these alkylithiums get with each alkyl group that you add to that carbon atom. So T-butyllithium is the most reactive alkylithium we have in our lab. You know, most labs have a bottle of tert-butyllithium. It's so reactive that each drop of the solution that touches air rips a proton off the H2O molecules. Your air you're breathing right now has water vapor in it. And tert-butyllithium will rip those protons off the water molecules so aggressively that the heat ignites the solvent. So it's highly pyrophoric. So I don't have any examples of alkynyl lithiums. We usually make those by deprotonation. But it just says that if you took butyllithium and you mixed it with butyl iodide, you'd get a 1-to-1 mixture. Nobody does that. If you want to make if you wanted to make an alkyl lithium like this, from an alkyl iodide like this, you'd start with a more reactive alkyl lithium. Usually you'd go straight to T-butyllithium. So if you take T-butyllithium and you take alkyl iodide, it would push the equilibrium to that side because it's a stronger alkyl lithium compound. It's a more reactive carbon-lithium bond. Okay, so usually we use butyllithium, but if we want to if you want to take an alkyl iodide, we would probably use T-butyllithium. If we just wanted to make certain that we were driving the equilibrium this way, no questions, we would use T-butyllithium, which is more expensive and more of a hassle to work with. But sometimes you don't want to dink around with your equilibrium. You just want to drive it all the way really quickly. Okay, so again, we don't take lithium metal and mix it with alkyl chlorides or iodides, or maybe you might do that with Grignard reagents and magnesium in a sophomore organic lab. But if I want to make something that is a hardcore nucleophilic carbon metal bond, I'd go get the bottle of tert-butyllithium and just deal with the pyrophoricity if I wanted to do that. All right, so metal-halogen exchange. Now it is very rare for us to deprotonate CHs to make alkylithium compounds. Enolates are a different issue because they're next to a carbonyl, but if I just wanted to deprotonate one, that's not typical. I'll show you a couple of reactions here where you can deprotonate CHs using alkylithiums, but usually there's some sort of a trick thing. You're not actually purposely making an alkylithium in this case. Here's a reaction where you're pulling a proton off using a lithium amide base. And let's go ahead and talk about what's happening here, because I don't think it's obvious. You can see that you're forming a CC bond, but what is probably not so obvious is that you're removing a proton from here. Right? We don't always draw our protons. We very rarely draw our protons. I expect you to know exactly how many protons there were on every carbon in the starting material with one glance. You need to be that fast at making that interpretation. What's going on in this reaction? There's some sort of a base reaction that's going on. I hope you would guess that because it's butyllithium. Now when I look at a reaction and I don't know what's going on, I try to pick the most reactive species in there and try to make that part of my first arrow pushing. So what's the most reactive species? Is it the epoxide or the lithium amide? I'd say it's the lithium amide. And what's the most reactive part of the lithium amide? It's the lithium. Lithium wants 8 electrons. That lithium only has 2 electrons. My first step here is going to be this. There we go. And you kind of already knew that because that's what we do when we deprotonate to make enolates. You didn't actually know that, but you could rationalize it. Man, that lithium wants 8 electrons. Now we're starting to draw out something that makes sense here. Let's go ahead and draw that epoxide. I'll draw that lithium coordinated. Still doesn't have 8 electrons, but it's better than it was before. This is kind of starting to look like deprotonation to make enolates, kind of, right? That negative charge on the lithium makes the lone pairs on that nitrogen more reactive. Let me circle that charge because it looks like a bond there. There we go. That O+, the positive charge on that oxonium on the epoxide, that makes it easier to break the bonds to the epoxide. So maybe it makes sense now that we've coordinated that it should be easier to now deprotonate. And it turns out that this elimination occurs syn. Because the epoxide is, if the epoxide is up, you're going to deprotonate the H on the same side. There's 2 protons on that carbon. You're going to deprotonate the proton that's up, like the epoxide. If the epoxide were down, you'd be deprotonating the H on the bottom side. This is a syn elimination. Nobody knew this was a syn elimination until Thummel did some deuterium labeling studies to show that it's the H that's on the same side of the epoxide. And that shows that oxygen-lithium cyclic transition state is critical for this reaction to occur successfully. Okay, so so you can deprotonate, you can do eliminations with epoxides. The strain ring wants to open, and it's a syn elimination. Now let's go ahead and talk about what happens in this case, because this is an example where if you go into the lab and you're just trying to synthesize something through a 9-step synthesis, you just want to get your product and move on. And here's a case where somebody got a 16% yield, and thank goodness they looked at what else was going on in the reaction. Usually you just isolate your product, you move on, and then you don't look at what else is going on. But that's not the major product in this reaction. Let's go ahead and draw out the major product in this reaction. Here's the major product in this reaction. How many of you would have guessed this? Right? You got to draw some pretty crazy arrow pushing if you're going to predict that you formed a CC bond right in the middle of our 8-membered ring. Right? That means somewhere in this mechanism we're going to have to do something with one of these carbon atoms over on the other side. So let's go ahead and talk about what's, now that you've seen that previous mechanism with the cyclopentane epoxide, you can kind of guess the first step is going to involve some kind of coordination to the epoxide. But instead of deprotonating here, right, that's only 16% of the product. There must be some other deprotonation that's occurring. Right? So let me go ahead and draw out this bond here. Right, once you make that bond there, it turns out that you can also, in this case, start to see competitive rates of deprotonation right on the epoxide ring. Right here, or on the one below. That lone pair on the amide can start to pull off, right? This lone pair on that lithium amide base can now start to pull off protons. Wait, do you get the allylic deprotonation? Yes, you do. That's 16% of the product. But the main product here, in 70% yield, is this cyclopentene. So what's the ratio of deprotonation allylic, or I guess it's not an allylic system anymore, but what's the relative rates of deprotonation there? It's 70 versus 16. What is that? I'm not good at math. That's like 5 to 1. So 5 to 1 ratio. You can convert that into kcals per mole. One transition state is what's a factor of 5? It's like 0.4 plus 0.4, a little more than 0.8, 0.9 kcals. One transition state is like 0.9 kcals per mole, lower in energy than the other. So it's the transition state for deprotonation on the ring in this 8-membered ring system is a lower energy transition state. Let me go ahead and draw out what happens here in this case. You'll end up generating this species, and I'm going to try to, let me see if I can figure if you know you're going to make an 8-membered ring, right? One way to draw an 8-membered ring is to draw it as that stop sign octagon shape. But another common way to draw 8-membered rings, if you know you're going to do stuff with the middle of the reaction, is to draw 2 5-membered rings. I'm going to draw 2 5-membered rings connected to each other, and let me just kind of emphasize the epoxide here. And then I'll erase a bond. So I'll draw 2 5-membered rings connected here, and then I'm going to erase that bond in the middle. Whoa, that wasn't a very good erase. Man, my erasing is not very, I gotta have a better way to do it. Let me draw You can just pretend I erased it because I don't have a highly precise eraser here. Okay, so there's my two 5-membered rings. You can't even tell there's a carbon in the middle. That's the crummiest drawing. I'm sorry for not doing a better job there. So there's my epoxide. And I've deprotonated here, right? To make a carbanion, some sort of a carbanion when I pull that proton off of there. I've got some sort of a carbanionic species. It is easier to make carbanions on strained 3-membered rings than on just regular alkanes, right? The bonds in the middle of a 3-membered ring are more nucleophilic, but the bonds on the outside of a 3-membered ring are easier to deprotonate. And you could see that in that table for the lithium-halogen exchange, that cyclopropyl anions aren't as reactive as regular alkyl anions. They're more stable. Okay, so you deprotonate here, and this is what you could not have guessed. What you couldn't have guessed is that once you get to this species here, I'm not going to put the lithium on there. Let me just because I'm going to end up with more stuff to explain to you once I start telling the truth. It turns out that bond right there next to the carbanion can pop off. Who would have thought that, right? That carbanion is not stable, doesn't like the negative charge, but it turns out that can pop off. Until you'll end up with this species here. Let me, boy, I'm really diverging from the way that I initially drew this out. You'll end up with this species here. That's not negatively charged. It's got negative and positive charge, and now there's an empty p orbital. There's these original electrons that are sticking out in this sp3 type orbital. Now that would be in an sp2 type orbital. But there's also an empty p orbital now. It's like a carbocation. It's like a carbanion and a carbocation. Plus charge and minus charge makes 0 net charge. Man, this is an incredible... Is it a nucleophile? Yes. Is it an electrophile? Yes. It's both. We call this a carbene, and typically this will exist. It doesn't matter how you get to the arrow pushing. There's more than one order of steps here. You'll eventually have this species that has that lone pair attached to the lithium. It's still nucleophilic, but there's an empty p orbital on here. It behaves kind of like an alkylithium, super basic, super nucleophilic. It behaves kind of like a carbocation. We call this a carbenoid. It's not, you know, carbenes are usually neutral species, but this species is called a carbenoid, this species here. And it turns out that carbenoid is so reactive. Let me draw a different, I'm not doing the best job of drawing this carbenoid. Let me redraw that carbenoid species. I'm going to draw it so that we can tell that across the ring from that empty p orbital, there are CH bonds. And this is the problem with medium-sized rings like 8- and 9-membered rings, is that if you have these species like carbocations on the other side of these CH bonds, you can't get away from those CH bonds on the other side of the ring. You can't get away from them. And those CH bonds on the other side of the ring are being pressed, it's called a transannular interaction, into this carbenium ion, and you'll end up with an insertion process. The electrons here will end up attacking. So the carbon-lithium bond, the H will come in and attack. Let me try to make some room here. I'll draw it coming from the top. Will come and add in, and at the same time that highly nucleophilic carbon-lithium bond will attack the carbon on the other side. And that's what leads to this formation. And the H that used to be on the other side here, there used to be 2 H's. Whoops, let me do it in black. There used to be 2 H's here. I'm trying to draw it in black pen. There used to be 2 H's here. One of them is still there. That other H has now moved over to this other carbon on the other side. You know, if they hadn't isolated this other product, nobody would ever have known that this interesting chemistry is going on. Try to stay curious if you're ever doing organic chemistry about what the other things are that are appearing in your reaction. This whole carbenoid thing is not anything you would have expected, and it doesn't typically happen. Actually, it does typically happen. You wouldn't have known it was happening unless you had this 8-membered ring system with the transannular interactions. Okay, generally, we don't just take butane and deprotonate it with alkylithiums. That's not really a possible process. It's not realistic. It's completely unusual. When we make alkylithiums in the lab, lithium-halogen exchange is the simplest and easiest process. We've got a few other tricks to make alkylithiums, but you don't typically just deprotonate things with butyllithium. And the reason I'm now remembering why I put this here is you can also do these reactions with butyllithium, and you'll get even more complex results. I want to introduce our next topic. Let me introduce our next topic here. We don't have a lot of time here because a lot of you have to leave for another exam. Let me try to take just a couple of minutes to intro what we're going to start talking about, and I'll start fresh next time. If you've taken an introductory class in organic chemistry, one of the first carbonyl reactions they teach you about is the reactivity of hydridoaluminate reagents and hydridoborate reagents, nucleophilic bonds to H, adding to carbonyl groups. And these are some of the most complex mechanisms in organic chemistry. I don't know why they start off with that. And when we come back on Monday, we'll talk about the mechanisms for these reactions and what kinds of shenanigans you have to go through if you want to turn a carbon-hydrogen bond into a good hydride donor. What do you need to do if you want to get a carbon-hydrogen bond to start doing stuff like sodium borohydride and lithium aluminum hydride? We've got some tricks up our sleeve that we can apply to make that happen. So we'll review reactions of tetrahydridoaluminates, tetrahydridoborates, and then we'll talk about some cases where carbon hydrogens, carbon H bonds can add, and some other species.